Dear students, let us learn the properties of haloarenes. Unlike haloalkanes, haloarenes undergo only two types of reaction. One is electrophilic substitution reaction, which we have recently done while doing the properties of benzene. It is very similar to that. And reaction with metals. The reaction with metals is very similar to that of haloalkanes. So, if you check the resonance structure of chlorobenzene or any of the haloarenes, you can see that haloarenes are electron donating groups. Okay, the halogen with the three lone pairs, they are electron donors, which makes the ortho and para positions electron rich. So when they are treated with electrophiles, the electrophiles will get introduced in the ortho and para positions. So they are ortho-para director. So let us have a look at the reactions. But one thing you have to understand that halogens are little more electronegative than carbon. So though it is donating the electron to the ring, but at the same time it is pulling the electron from the ring also because of more electronegativity. But ultimately the free electrons of the halogen, they can be donated easily to the ring. Hence ultimately it is an electron donating group. But whatever it is, due to this electron pulling effect of the halogen, the electrophilic substitution reaction do occur, but with little more difficulty. Okay. So you can see here the 5 reactions. Normally, as I told you, in all the chapters we'll have these 5 set of reactions: halogenation, nitration, sulfonation, and Friedel-Crafts alkylation and acylation. Now in this halogenation reaction, as you know, we need a halogen. The halogen could be either chlorine or bromine, and you definitely need a Lewis acid catalyst such as anhydrous AlCl3 if you take chlorine, or anhydrous AlBr3 if you take bromine, or you can take aluminium with chlorine also, iron with chlorine, and you can replace it by bromine. But make sure that the reaction is carried out in the dark. Okay, that is why it is different from the free radical halogenation. So since halogens, these haloarenes are ortho-para director, so the incoming electrophile will occupy either the ortho position or the para position. Okay, if it is chlorine, then you have to write chloro. If it is bromine here, then you have to write bromo. And definitely the para product is major product because of, as you know, these two halogens are far away from each other, so they suffer minimum repulsion. The next reaction is nitration. So you know that for any nitration reaction, we need the nitration mixture, which is a mixture of concentrated nitric acid and sulfuric acid, and the electrophile is NO2. So the NO2 gets introduced in ortho and para position as similar to that of halogenation. Then comes sulfonation. For sulfonation reaction, you know that concentrated sulfuric acid dot SO3, which is also called oleum. Together you may write it as H2S2O7 as well. So what happens here? This SO3H group gets introduced in the ortho and para position, and you know SO3H group is called sulfonic acid group. Now next is Friedel-Crafts alkylation and acylation. For alkylation, again you need Rx dash. Why did I write X dash here? Because this X and this X need not be same. They may be same, they may be different, and accordingly again you need anhydrous AlCl3 or AlBr3 depending on the halogen. The idea is you need a Lewis acid catalyst. So the alkyl group get introduced in the ortho and para position. Remember, the halogen will remain in its own position in all the products, you may note. It is the incoming electrophile which will come in the ortho and para position because the halogen out here is electron donating group. Now when you do acylation reaction, this acylation reaction, what you need? You need a acyl halide, RCOX dash, and it gives you a ketone, COR dash, and if this R dash is CH3, we call it acetophenone, and if this X is Cl, then we call it para-chloroacetophenone and orthochloroacetophenone. So these are the 5 set of reactions which we will encounter in all the chapters of wherever we do any arene compound, whether it is haloarene, whether it is phenol, or whether it is aldehyde ketone, whatever we do. Next, we move to the reaction with metals. By the way, one thing you may note here, that the halogenation reaction and Friedel-Crafts reaction, they require the Lewis acid catalyst. Now, the reaction with metals is very similar to that of haloalkanes. The two reactions, one is with sodium, another reaction is with magnesium. In haloalkane, the reaction with sodium, we name it as Wood's reaction. But when we use haloarene, the same reaction is known as Fittig reaction. Reagents are same, compounds are similar, the products formed are also similar. So here you see what we have taken. We have taken chlorobenzene treated with sodium, and another chlorobenzene we have taken, and the medium has to be dry ether. And what happens if I draw a box? These two chlorine will go away with sodium to form sodium chloride, and two benzene rings will be connected by a single bond, and the compound is called diphenyl or biphenyl. If you check the conversions of in the exercise, you will find there are questions where how you prepare biphenyl is there. So this is definitely one of the steps which you have to follow. Now you have seen here in Wood's reaction, the haloalkane was similar haloalkane Rx plus sodium, and another molecule of Rx we write as XR. And in Fittig reaction, you can see here the chlorobenzene and chlorobenzene we have just written by facing them each other, and sodium is there in the middle. But now if we combine haloalkane with haloarene, then the name of the reaction becomes Wood's Fittig reaction, and here we get a combination of arene group with the alkyl group, and the product out here what we got is toluene. This is also a very interesting reaction for conversion. The next reaction is with magnesium, and as you know, with magnesium we get Grignard reagent. So I told you how to remember. Just put magnesium in between halogen and the aryl group, and the product formed out here is phenyl magnesium chloride. If you have Br here, then it will be known as phenyl magnesium bromide. Now this Grignard reagent, if you treat it with water, it will get converted to benzene. So if you remember, we have discussed earlier also that all Grignard reagent reactions should be done in dry ether medium. There should not be a drop of water. So as you can see here, this can be a conversion. How do you convert chlorobenzene to benzene? So how will you do it? First you have to treat chlorobenzene with magnesium followed by hydrolysis. Now the question arises, if you remember, when we did the properties of haloalkane, we have done so many reactions under the category of nucleophilic substitution reaction. You can see here one of the major reaction which haloalkanes undergo is nucleophilic substitution, under which you have done Sn1 and Sn2. And if you check the examples, we have done around 8-9 reactions here. But why do in haloarenes we don't have such category of reaction? Why nucleophilic substitution reactions, which is so very common in haloalkane, why is it not popular in haloarenes? This is a very, very important question. To answer this question, let us look at the factors which is responsible for not having nucleophilic substitution reactions in haloarenes. Please listen to them very carefully. You may have noticed that whenever nucleophilic substitution reaction occurs, this bond has to be broken. The bond between carbon and halogen needs to be broken. Now, if the bond enthalpy is very high, the reaction will occur with much difficulty. So that is what is happening here. You see, it's written here, bond enthalpy is inversely proportional to bond length. That means larger the bond length, less will be the bond enthalpy. So the factors which are responsible for these reactions not to happen is mainly resonance and hybridization. Let us see how does resonance and hybridization affect not to have nucleophilic substitution reaction so easily. When we draw the resonance structure again, you may have noted that out of these 5 structures, in 3 structures, the carbon and halogen bond is having a double bond character. And when we see the resonance hybrid, you can see there is a partial double bond character between carbon and halogen. Now, when there is a partial double bond character, definitely the bond length is less because double bonds are shorter than single bonds. Now when the bond length is short, bond enthalpy will be high. So it will be very, very difficult to break these bonds to carry out any nucleophilic substitution reaction. So that is one of the factors. The second factor is hybridization. In haloalkane, in CH3Cl, suppose the carbon out here is sp3 hybridized. But in haloarenes, the carbon out here is sp2 hybridized. So you know that when the hybridization changes, the S and P character also changes. So in sp3 hybridization, the S character is just 25%, and in sp2 hybridization, S character is 33.3%. And we know that more is the S character, closer to the nucleus, and shorter is the bond length. So both resonance factor and hybridization factor contribute to the shorter bond length of the carbon halogen bond, which makes it difficult for the cleavage of the carbon halogen bond. As a result, nucleophilic substitution reactions are very less common. Now let us have a look at the possibility in case they undergo nucleophilic substitution reaction. The possible pathways are either Sn1 or Sn2. Now let us see the possibilities of Sn1 and Sn2 reactions. You know, Sn1 reactions are governed by stability of carbocations. Now let us assume that the benzene ring which we have, suppose the carbon halogen bond is cleaved. Now if the carbon halogen bond is cleaved, what will be left with? Will be left with a phenyl carbocation. Okay. Now it has been found that this phenyl carbocation neither doesn't attain any stability either by resonance or any other factor. So since the phenyl carbocation is not stable, Sn1 reaction will not occur, because remember, Sn1 reaction is governed by stability of carbocation. Okay. So let us give up the idea of Sn1. Now let us see what is the possibility of Sn2. You know that in Sn2 reaction what happens? If you have this halogen, suppose CH3Cl, and you are treating it with the nucleophile always attacks from the back side or rear end, okay? Because the nucleophile carry negative charge and the halogen also carry negative charge, so it cannot approach from the same side, okay? So it always attacks from the opposite side because it will suffer less electron cloud and less repulsion. But what happens when we have the benzene ring? You see, in addition to the lone pairs on the halogen, there are 3 pi bonds. There are 3 pi bonds in the benzene ring. And you know, these pi bonds are not localized. They are not fixed in one place. So we show them like a circle, if you remember. So this is called pi cloud. So you can see the unhybridized p orbital on carbon, because carbon is sp2 hybridized. So out of 3 p orbitals, one of the p orbitals is free, and that is the p orbital which is responsible for pi bond formation. So this 6-membered ring is there, and the pi clouds are above and below the ring. Just this 6-membered ring is like a sandwich between the pi clouds. So if a nucleophile tries to approach from this side, what will happen? It will encounter the electrons, the pi electrons. So electrons on the benzene ring and electrons on the nucleophile, they will suffer repulsion. So the approach of the nucleophile becomes difficult even from the back side. And that is why possibility of Sn2 reaction is also ruled out. Okay. So because of these reasons, these 4 reasons, the nucleophilic substitution reactions are very, very difficult in case of haloarenes. They are difficult but not impossible, which we will see in the next video. Thank you.